Okay, so now we're moving on to the second phase of the class, and that is the concept of external flows. External flows is the types of scenarios where you have maybe a boat sitting in water. So this is all water right here. It's moving at some velocity. And we are always trying to calculate the drag force based on the flow that's running parallel. That's the classic setup for external flows, right? Before, this fluid's on the outside of on the surface. Before, it was about fluid moving on the inside of pipes, right? So this is, you can see internal versus external. So first thing before we get into all this, it'd be nice to just show you the similarities of what we did before and how we're just going to do the exact same stuff for the external, motivated by the same stuff. So for the internal flow, right, what we did was we found the flow field. Right? And this had two cases, right? It was laminar. The U of R came from, right? So, right, some people say first principles. If it was turbulent, right, sort of UR was just given by experiment. All right, so sort of this phase one of this analysis was trying to determine this flow, right, determine this flow field or velocity as a function of a coordinate. Then after that, right, we took that and we calculated these quantities that became helpful, right? Then the friction factors, right? So these are sort of these engineering quantities that we then used the U of R to calculate. Right? Then the last step you did was then you used all those things to calculate energy. Right? So this is this. Right? This is just the pressure for rho G, right? So that's what we just did in the first five, right, for the first 5 lectures. We're just changing the names of things now when it comes to the external flow cases, right? So for the external case, we're going to determine something called the boundary layer, right? Boundary layer. And there's a case that will be for laminar. And a case for turbulent. Now this boundary layer has a lot of, right, this boundary layer, something called, it's actually, where is it? Delta. Okay, you don't know what it is right now, but then you're going to use this, right? You're going to use the boundary layer information to calculate things like shear stress at the wall, drag forces, something called a displacement thickness. You don't know what that is yet. Lift forces, momentum, and then momentum thicknesses. So these are other sorts of quantities. We're going to use this really flow field to calculate. And then what's the last step? We're going to use those use these quantities to calculate some energy, right? So really the energy, right, in terms of energy or power, we're looking for how much energy do I need to overcome drag. That is the burning question for external flows considerations, right? There's forces based on the viscous nature of the fluid. We do this analysis to come up with an energy requirement for how much do I need to get through the fluid. So that's the plan. So before we get into it, I think it's helpful to begin where all the experimentalists began and just go over some of the weird things that happened when you did some simple experiments for this external flow field. So the simplest one was people just had vents of air. So there's some vent of air. Air's flowing through some sort of vent. There's a fulcrum force balance. This thing came out. You put over here, you could just put a sphere or some object, some blunt body object that was sitting over this flow field. It's important, right? You put some manometer to measure pressures. So that's a pitot tube. What else I had? So this is force balance. Okay, so there's a force balance right there. So that allows you to measure force. You can measure pressure. If you know the pressure, this is a measure, right, of speed. Right? This fluid's one where you use pitot tubes. Airplanes, they have this pitot tube in the front to measure how fast they're going based on the pressure they measure. Same concept. So what you do is you then just fill in this graph when you do this experiment. Again, this is external flow because the air is moving around the sphere. So it's a great experiment to describe that. You make a graph of just speed and then force. So you're looking at the drag force based on how I ramp this speed up. Okay, and this is what people found. Section where it's going up. It does some weird wibbly wobbly. And then it goes back up. So this is not what we expect to happen, especially because there's this transitional range right here. What's happening is this area right here is at slow speeds. Right? And then here you can see that there's really fast speed. Some transitional regions, there's a drop in the drag force all of a sudden. That's pretty weird. The other thing is if you just compare these two curves themselves, because this can be drawn back to zero, right? This one grows much slower, right? This function is actually slow growing. This one's fast growing. So that's just not what you'd expect for some experiments like this. And it's a pretty simple one, right? All I'm doing is I'm just increasing the gap, I'm just increasing the air, I'm just increasing the speed of the blower that I have. It could be a hair dryer. And they have these huge motors that can get up to like hundreds of miles per hour, which is fascinating. But you always got this plot that would come out where it starts off slow, there's no drag force, it goes up pretty quickly. It drops down this kind of oscillatory range, and then you get back on the curve, which is steadily increasing. And the difference of these two, this is like comparing if this quadratic right here, this quadratic right here is sort of like, let's say it's 5 x squared. So the 5 out front kind of measures the curve, measures how steep it grows, right? This part right here, right, turns out to be more like comparatively like 0.3. So it's not, right, so it's actually much slower growing in terms of the drag forces when it comes to just increasing the air going through here more and more and more. So that's the simplest one. You could do that one at home if you have the right equipment. I think it's fascinating. And they did a bunch of other ones too. It didn't matter what you put on that force balance, right? It's a good experiment because this is just some attachment. So you could put a sphere, which is what they did a lot. You could put these teardraped right? These like teardrape type things on the very edge. You could just put like, you could put a square over that vent and you could then measure how those graphs change, but they all have the same behavior, which is that sort of, right? They all have the same behavior, which is the speed goes up. It's always like that. So that's really weird. So there's a lot of things to study. Then they started comparing bodies, which is really non-intuitive.